Não, mas esse não é pode fazer. Está comigo, está comigo. Eu posso fazer também.
Okay. So can everyone in online can hear us? You have to answer in the chat. Yes. Okay, everyone, let's go back to the second part, the afternoon part. So now we're gonna have our friend Gabriel here. He's gonna talk a little bit about his job, and he's also a master student here under the supervision of also Professor Elcio. So, Gabriel, all yours.
Good afternoon, everyone. As Bruno said, I am a master student here at USP, and I am working with Professor Elcio. Um, I'm gonna talk about my uh, work here. So, você passa para mim? Mais fácil. Ah, esse... Olha. So, in summary, um, my work focus on creating a data pipeline for analyzing the polarization of the bingo dish. And for this, I use simulations from Grasp, which simulate the bingo setup. Here is a image from Grasp. Here is the bingo arrangement with its dishes, and I am using a old arrangement of bingo here that are described in the bingo paper 3. And the Grasp is a tool for analysis and design of reflector antennas, and it uses physical optics method to calculate the reflected electromagnetic field. And here's a grasp output for a linear X polarized beam, Gaussian beam. And as we can see here, the X component are the beam, and the Y component are there is nothing here as we expected for a linear X polarization. And uh, my main tools are the Stokes parameters and Miller matrix. Here we have a schema for the Miller matrix, and here are the Stokes parameters. The Stokes parameters are used to represent Stokes states of polarization, and here are the representation of the Stokes parameters for that being I showed earlier. And this equation represents how the observed Stokes vector um, is uh, uh, this represents how the Stokes vector that interacts with the system are transformed to the observed Stokes vector. In this work, I used this states of polarization, and I defined these vectors by using these states of polarization, S1, S2, S3, and S4. And as we can see, we have a vector that have zeros in its components, except to except to one component that are one. And using vectors, those vectors, using that this equation, uh, I can uh, found the Stokes vector one observed by the Bingo telescope for that beam, represented by the Stokes vector S1, and it's the other Stokes vectors right here too. And as we can see, um, the results are the Miller matrix columns for each one Stokes vectors observed. And as Miller matrix is a linear transformation, we have that we can write the Stokes 1 prime as a average of the Stokes vector for a linear X polarization observed plus the Stokes vector for a linear X Y polarization observed. And we can build these vectors S1 prime, S2 prime, S3 prime, S4 prime, as we can see over here. And if we put these vectors side by side, we will obtain a matrix that correspond to the Miller matrix right here. And this is the result is it the Miller matrix I was able to generate. Briefly describing it, the diagonal components of this matrix represent how much of polarization mode passes through the optical system without being altered. Meanwhile, the off-diagonal components show how much these polarization modes are leaked in other modes. Remember, um, that is, this matrix does not correspond to the current bingo setup, and this entire process will be applied to more realistic simulation data of bingo. And I forget to say, um, here's the Miller matrix scheme, and um, I said that. Here is the one-dimensional cut in the maximum. Here we can see more details of the Miller matrix. Um, the details we can see is that the diagonal components are uh, more intense than the off-diagonal components. And for next steps, Uh, I currently working on Zerk models for the millimetrics components, and uh, I didn't put it in my presentation because for the time of these presentations is and the these plots are not completely finished yet. So thanks for the attention. Um, if there are any questions, I will be happy to answer them.
Hi, Gabriel. Pretty nice, good work you have presented now. Can you show us again some previous slides that one where you showed the level of the mixed matrix? Yes, but it's also mixed matrix. Because, for instance, when you see diagonal results, we have a whole bar, not a whole bar, but color bars. When you take a look on the off the Venn diagonal, we have others. Can you expand the level of these signals because we cannot distinguish by eyes from here uh, if it's relevant or not the level of these signals by the off diagonals, you know?
The scales of the
Yes.
color bar
Hmm.
are in different scales, but the maximum is 40 decibels. Uh, and we can see the details of this difference in this plot. It's better to visualize this difference.
So, mm, okay, so in the right panel you have s- the IKUV, and it's basically the each column, right?
Yes, blue are the
If
I
each
to
we
Y
I to
prime.
I,
Red are the uh,
Q
K,
Q to
Q,
I.
Q to Q prime. Yellow is the U to U prime, and the green is the V to V prime.
Okay. Okay. Nice. Thanks.
So any more questions? Okay, thank you very much, Gabriel, for your presentation. So let's continue now. Let's go to our second person for the afternoon. That is Clécio. He is from Paraíba, and he will show us his work. You have to give permission to him also to speak. So, Clécio,
Okay. Now, can you hear me?
yes,
Okay. Just a minute. Mm,
I think you can share your presentation.
Okay. Can you see the presentation?
Yes, however, your volume is a little low.
Oh, just a second. And now
Better.
it's
Okay,
better?
yes.
Okay. Okay. So can I start the presentation or?
Yes, you can start.
Okay. So,
Hi, I'm Clécio from UFCG. I'm postdoc here in Paraíba, the city Campina Grande, and I will talk a little bit about the model reconstruction methods from real data. This presentation uh, should be longer, but I am trying to resume the main information for you. Okay. Um, okay. So, an introduction. I will introduce you to the problem we are studying because the a problem we have now in the modern cosmology is the expansion, the accelerating expansion of the universe. Then we have many theories trying to explain this acceleration, but we don't know what is happening. So the nature is different of this phenomenon is still unknown, as I said, and we have more problems every time when I goes deep in this theme because in recently in the cosmology the Hubble constant tension was aroused for us because we have a discrepancy in the measure in the value of this constant as we use the CMB data, cosmic microwave background data. We find on value, and when we use the supernova data as an example, we find another value. And if it is a constant, it should not be true, but that is the problem, the real problem. Mm, Then we propose a reconstruction method because this method we can use not so much points and it can find a relation between the data. Then we have as an example FRB data or supernova data. We can relate both by using this method. And this method reconstruction and function, we don't need in principle in the beginning, so we don't need assume and model and cosmological model as an example. We are studying two different methods now, and it is scaled refun, reconstruction function, artificial neural networks, where we use artificial neural networks, and the Gaussian process, the second one. But what is refun? Refun is a process where we use artificial neural network, and it simulates biological neurons, artificially, of course. Um, the aim of the this method is to construct a function that can relate the input data and output data in a function and provide an association between the points and the function. I will show you in this presentation how it will work. And then we can find some connections, the best connections between the point where we put in the artificial data and the result where we expect it to be connected with one function. This code was developed by Wang et al. And they called it have construction functions with ANN. Because of this, we said refund. Mm. So how it works? We have layers in this program, and each layers receive an vector, and these vectors are distributed in another layers, and we have an activation function where the activation function used in this program is this form, and this parameter alpha, this alpha parameter is a positive hyperparameter, and this hyperparameter is responsible to controlling the value of this method. Here is a description how it works. We have Redshift as an example and put it here. And the vector is distributed to the hidden layers. And each hidden layers will work alone in the beginning. And after that, it will give us two results. One result is the variable parameter, and the second one is the error associated to this method. Okay. So the optimization of these hyperparameters are made by using a function called loss function. And the loss function is the sum of each observable data minus the predicted data. And this observation data is calculated by using cosmic chronometers. It's a method where we do not need any model, any cosmological model. We just use this approximation where the difference of the redshift and the cosmic time are needed. And okay, this is the first method. The second method is the Gaussian process. Here we want also to reconstruct a function, but this time we use on process based in the Gaussian process algorithm. Because of that, we say Gaussian process in Python, GAP. This is a generalization of the Gaussian distribution, but it describes a distribution over functions, not in random variables. And this function generated by the Gaussian process returns a Gaussian random variables. And the functions generated by these different points are not completely independent. The points, we have 2 points, the x and x prime as example, and but these points are related by a covariance function. And the covariance function is given by this equation 4, okay? And there are 2 other parameters, sigma f and L. And these parameters are hyperparameters, where used to calibrate the Gaussian process. It's similar to calibrate. Okay, these hyperparameters are optimized by the maximal marginal likelihood. Is this function? Here we have a lot of matrices. So matrices. And then after that, we can find a relation between the initial point and the final point. Okay. We applied these two methods in fast radio bursts. As Professor Elson said earlier, fast radio bursts are mysterious signal where we don't know so much about this signal, but it is an extragalactic signal. And we don't know well the source and how is the process, the creation process of this phenomenon in the nature. So uh, we want to as we want to study cosmological problems, we have to use we want only the distribution measure of the external source. That is the M, the galactic medium, the spectrum measure of the intergalactic medium, and the galaxy host. However, this the MHM, the galactic medium, we need the Hubble parameter, and then we can use the Hubble parameter for reconstruction methods to and apply here in the fast radio burst theory. The uncertainty associated to this theory is given by this equation, okay? And we arrive at this result. This is our initial result, also is an example. Here we used 64 localized FLBs, and we made the MC, and we can see that the gap, the Gaussian process, and the refund uh, leads us to a similar result, but is a well result also. Here we have the numerical values of this analysis, where we can see that the Hubble constant is in a only used here. We only used fast variable burst data, okay, and we give a good result to Hubble constants. And we can see that they are a little bit, no, it's similar, it's not so different, but it's both methods show us that are good to work with fast radio bus because we have uh, so small points. So there's we have not so big data to work with, as we have in and supernova data is an example. And the final comments, for the small FRB data set, the reconstruction model could arrive at a good result. And then we expected that also, with a much larger data set, a better result comes and with minor errors. Both methods leads us to a similar result in this case, but with a larger number of FRBs in the future may be evident, maybe so could be more evident the difference between the methods, and we can choose the better method to study FRB. Um, I would like to thank the FAPESC because of the support, the financial support to my research. And this is the basic bibliographic reference to this presentation. And thank you for your attention.
So thank you, Clássio, for your presentation. Does anyone have any questions for him? No. No? Okay. So thank you again, Clássio. So since you
Thank
have
you.
permission to Lucas. Okay, so our next presentation will be hosted by Lucas. He's also from UFCG, and he will talk about his work inside the Bingo project. So, Lucas, we're gonna give you the host, and you can start your presentation. Can you hear us? We are not hearing you, Lucas. You're muted. Ainda tá mudo, Lucas. Tem que desmutar o microfone do Zoom.
Acho que tem algum problema a mais também. Problema.
Acho que eles estão com algum problema.
Oi?
Acho que você tem que dar permissão.
Eu já dei permissão. Mas eu faço aqui.
Pedir para ativar som. Qual pedir para ativar som? Tenta agora, Lucas.
Ok.
Ok?
Okay. Hello, my name is Lucas Santana. I hold a degree in physics from the Federal University of Bahia. I'm currently a master's student in physics at UFCG under the supervision of Professor Amilcar Queiroz. I'm also pursuing a master's degree in electrical engineering at UFCG. At Bingo, I have been working alongside Rafael Batista in the instrumentation area, focusing on the SCARAB system, conducting tests and collecting data about it. This presentation titled Mapping of Electromagnetic Signals at the Bingo project site, preliminary results. It's about my visit with Rafael to the Bingo site at 18 December last year. The presentation will follow this structure. The location where the measurements are taken. And next, I will detail the equipment used in the measurements and the methodology adopted. And I will present the preliminary results obtained. Followed by the next steps in the measurements and the final remarks. About the location, the city of Aguiar is situated in the Sertão region of the Paraíba, within the metropolitan region of Vale do Piancó. Neighboring cities is São José de Piranhas, Coremas, Igaracy, Serra Grande e Itaporanga. And the distance from Campina Grande is 295 kilometers. Um, uh, if you can see my mouse, here is Campina Grande, and in red of the map is Aguiar City. About the equipment used for measurements, this is the Keysight Field Fox model 9 N9912A. It's a portable radio frequency analyzer. This frequency range is from 100 kilohertz to 6 gigahertz. Um, your key functions is uh, CAT, cable and antenna tests, to, to make tests about antennas. The other function is NA, network analyzing, and SA, spectral analyzing. We use the SA for our measurements, and other uh, recurse of the equipment is data saving. You use the CSV format for uh, we we data we data. Other equipment was the FP8 from the R&S. It's to a portable radio frequency analyzer. It has a touchscreen display, different from the Field Fox. It has a frequency range from 5 kilohertz to 44 gigahertz. It has a high resolution if we compare it the Field Fox, and it has a saving data too. Other equipment that we used in the measurements was the antenna HE400. It's a portable directional antenna. It means that it captures the signal in the direction that we appoint. The frequency range is 80 kilohertz to 80 gigahertz. The impedance of the antenna is 50 ohms. It's good because the compatibility of with other systems. They has they have it has it have it has DNSS receiver from obtain the GPS position and electronic compass to facilitate the location of the antenna angle. The methodology in the measurements. We connected the antenna to the FP8 to obtain the GPS position. Before it's connected from the FP8, we connected to the Field Fox to make the measurements. We configured the initial frequency to 50 megahertz and the final frequency to 1.6 gigahertz. The resolution bandwidth was 2 megahertz, and the video bandwidth was 30 kilohertz. The device was set to perform 10 points for everything. And to collect data, we in four modes: clear white, it's real time, basically, maximum, minimum, and average. We made the measurements in 9 directions and cardinal points. In this case, we positioned the antenna in 45 degrees angle from the ground. For collateral points, we positioned the antenna at a 60 degree angle from the ground. And the final direction was the zenith. After everything, it was 10 points of everything. We saved the data in CSV format. This picture is an aerial view of the site, Bingo site obtained from the Google Maps. And the marker the marker points indicate the locations when we made the measurements. In blue was in the basin, in red the helipad, in green P1, in yellow P3, in purple P5, and in orange external point. About the preliminary results, I have brought 2 graphs prepared by Jordan. This one is based on the data collected by the field fox at the location P5 with the antenna point south. Here you can see in blue the instantaneous points, instant points, in orange the maximum points, in green the minimum points, and in red the average. In this graph, we can see highlighting some points in radio and TV region from 100 megahertz to 400 megahertz. If you can see here in red a high signal. And another issue we can highlight is the presence of a step around 700 megahertz. This problem occurred due to poor choice in the device configuration of the equipment field fox. As other graph was captured by the FP8 in the same location. Here, the clear white and average data could not be saved. So here we have the maximum points and the minimum points. And we can see big signal in 400 megahertz. This is from Energisa, that is a local electricity company. We can see other signal in 800 megahertz, which are likely from cellular networks, and between 1.2 gigahertz and 1.4 gigahertz, we can identify GPS signal. The next steps are carrying out measurements in the anechoic chamber to obtain data in a controlled environment for comparison with previously obtained data and future data. We need to conduct a detailed reading of the equipment manuals to improve configuration and obtain better results. Performing new measurements around the metrology laboratory, LabMet here in UFCG, to compare with the data obtained in the anechoic chamber. And finally, we conducting new measurements at the bingo site. With the better configured equipment, we will obtain more concrete data. Our final considerations. The method used to perform the measurements was effective in some aspects. The configuration used for the equipment was not the best. We need to try other configuration. It's necessary to carry out measurements in the anechoic chamber, and new measurements need to be performed at the bingo site. That will be made early. That's my presentation. I finish here my presentation. Thank you for listening.
Thank you, Lucas, for your presentation. And if you want to ask any questions, Alessandro does.
Hello, Lucas. I'm Alessandro here. Thanks so much for your presentation. I'd like to ask you, well, two questions. First of all, we can pay attention in these final remarks. I'd like you to comment more, at least a bit more, what you mean like when you say configuration used for the equipment was not the best. Can you explain better what you mean like it was not the best?
Probably the step that has here on 700 megahertz probably was because the configuration of resolution bandwidth and video bandwidth. We are making other tests on the anechoic chamber to see if it is a property of the equipment or was the configuration, but probably was the configuration. Okay.
Okay, if I understood, uh, we, no, you can keep in that slide. Go back. Yes. Yes, this one. We cannot confirm that the equipment is configured in certain way that we can have the measurements in a confidence for the whole frequency range you're assuming here. Is it? Because, well, your measure from 100 megahertz, if you have seen well, until 1 gigahertz point 6. If your configuration is stable, well, that's okay. But maybe measuring some chunks can Quite some in there. But anyway, another question is because have shown us 3 points, P1, P3, and P5. Uh, what means this piece? The P's are the
Sorry. Uh, the these points, P5 is when where will be the horns, um, and had decline in that is divided in 5 steps. So we made the measurements in P5, P3, and P1. P1 is the ground. Uh, it's elevation in
Yes, I think it's
4 meters.
Lucas, this also speaking. It's a bit misleading in the design because where it is written telescopio bingo is not actually the telescope is in P1, P3, P5. And that spot is where it's written telescopio bingo is actually the external point only for the words telescopio bingo is general, it's just a title. Below is where is the base and helipad are the entrance to the compound. Maybe that's the question. So where is the telescope itself is the P135.
So, okay, I see. So maybe P1, P2, 3, and P5 means the position for the structure for 8 dishes and also the structure for the feed horns. Okay. Uh, by the way, I had another question here, but I guess I forgot. Uh, well, anyway, if I have some question, I can discuss later with you. Well, thanks so much.
Thank you.
Hey, Lucas, just out of curiosity,
I remember my question. Sorry. Show us
Uh,
5 measurements. Do you have measurements for the other piece?
no, we made measurements only in P1, P3, and P5. The difference between the floors, P1, P4, was a very
Time.
a little.
Yes, I got it.
So
I say because you want to show us the P5. So the question is because the P5, P3, and P1, they have the same answer for us in these measurements. Is it?
um,
Are quite similar for these 3 points, right?
you see, yes, yes, yes.
Okay, thanks.
Hey, Lucas, just out curiosity, what is the distance between P1 and P5?
Um, um, the engineer said me was it's about 40 meters.
Oh, it's very close. Okay. Okay, thank you.
Yeah.
Okay, so anyone, any more questions online? No. Let me see here. Online, no. No questions. So, guys, that's it for today. Thank you very much for your presence here. And as we saw, we have a lot of different branches. As we saw, we have a lot of branches here at the Bingo project. And we see each other tomorrow at 9, okay? A little bit earlier tomorrow. So, thank you again. Oh,
Yes,
yes.
the photo.
Jajun gave idea to have a photo of everybody. Also, people in the Zoom meeting, if you can open your camera, would be nice. So we can have a picture of everybody together. Vamos colocar o quadradinho com todo o Mas deve ter um jeito, não tem? Porque tá o Lucas aqui, né? Thank you, guys. See you tomorrow.